Electrostatic loudspeaker simulation in QuickField. Electrostatic loudspeaker consists of the disc diaphragm and two disc stators. DC voltage is applied to keep the diaphragm at a constant potential with respect to the stators. Audio signal voltage is applied to the stators in antiphase. And due to electrostatic attraction force, the diaphragm began to vibrate. Our task is to calculate the force and to calculate the diaphragm deformation. First, I am going to simulate electrostatic problem. I will apply voltages and calculate the electrostatic force. Then I am going to pass electric forces distribution from electric problem to stress analysis problem. In stress analysis problem, I will calculate the diaphragm deformation. To simulate electrostatic problem, I need to know voltages and the electric permittivities of all medias. And to calculate the deformation, I need to know the mechanical properties of all objects. The model features rotational symmetry, so I'm going to simulate two-dimensional problems. Okay, let's start QuickField now. In QuickField, I create new problem. Problem name loudspeaker. Next. The problem type is electrostatics. Length units are millimeters. And the model class is, well, every simulated device is a three-dimensional object. Loudspeaker features rotational symmetry, so I can use two-dimensional model. Model class is axisymmetric. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw geometry model here, or you can import the geometry model from the AutoCAD DXF file. In axisymmetric problems, the axis of rotation is a horizontal one, and I should draw only the upper half of the cross section. So I will add 2 points. Edit, add vertices 0, 0 and 0, 20. Close, zoom to fit, switch to insert mode, click and drag to draw the line. Stator disc cross section can be represented as a straight line. Line length is 20 millimeters. It's equal to the disc radius. Well, I have another stator. The stators are spaced 1 millimeter apart, so I will switch to select objects mode, right click, duplicate selection, displacement by 1 millimeter. Okay. In between the stator discs there is a diaphragm. I'm going to draw the diaphragm in more details. Diaphragm thickness is 40 micrometers. So again, right click, duplicate selection 0.5. Now I will move this selection 20 micrometers to the left, and I will duplicate this line by 40 micrometers to the right. Okay, let's zoom in. Again, switch to insert mode and draw the line here. And I should draw boundary at the bottom. Here. Okay, now let's assign labels. Through labels we will explain the geometric object's meaning and provide material properties. Switch to Select Objects mode. Click the object to select. This is air. Now click this object to select. Again, this is air. Click here, this is the diaphragm. This edge represents stator left, and this edge represents stator right. And there is a high voltage source connected to the diaphragm. So for this edge and for this edge, I will assign label high voltage. Okay. Now let's provide physical properties for these labels. Double-click the label name in the tree and type in the electric permittivity of the air, which is 1. The electric permittivity of the diaphragm is 3. Okay. High voltage source is 600 volts. Left stator electric potential is -50 volts, and right stator electric potential is +50 volts. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be constructed. Save all problem files and solve the problem. Let's take a look at the results. Here you can see electric field lines. You can adjust the field picture and switch on, for example, the color map of electric potential or the color map of electric field strength, and the correspondence between colors and numbers you can see in the legend. You can click any point using the local values tool to get exact values. You can specify point coordinates here. And you can use the contour tool to get the field distribution along the contour lines. Click and drag to draw the contour line and open the XY plot. Here is the electric field strength distribution. And you can get the exact values in the table. Coordinates, electric potential, electric field strength, vector components, and other field parameters. And you can use contours to calculate integrals. Contour clear. Let's zoom in. And I will click inside the diaphragm. Here is the diaphragm selected, and now I can calculate the integral. For example, the mechanical force acting on the diaphragm. It's pointing to the left and equal to 3 millinewtons. We have completed first part of our task. We have found the force. Next, we should find the mechanical displacement of the diaphragm. To calculate the displacement, I need to simulate stress analysis problem. Create new problem. Stress. Next, problem type is stress analysis. Length you need some millimeters, and the model class is the same axisymmetric. To be able to pass data from electric to mechanical problem, Both problems should be based on the same geometry model file. The geometry model file in electric problem was loudspeaker. So here I click browse button, and here is the file, loudspeaker. Open. Finish. Now this is stress analysis problem. The geometry model is the same and the labels are already assigned. But now I should provide mechanical properties for these labels. Double click the label name in the tree. Well, there is no mechanical stress in the air, so I do not specify any data here. Okay. And you see the exclamation mark. That means that this label is excluded from the analysis. For the diaphragm, Young model is 2 point. For the diaphragm, Young model is 5 gigapascals and the Poisson ratio is 0.4. I do not specify any force values here. I'm going to export forces from electric problem. Okay. These edges have no physical meaning in mechanical problem, so again I do not specify any data here. Just click OK and you see 0 mark. This means that this label doesn't affect the results. And again, I do not specify values for the left stator plate, and I do not specify values for the right stator plate. Now let's specify the link between electric and mechanical problem. Open the properties of mechanical problem, follow to the links tab, choose the data source type electric forces and browse for the problem. The problem name is loudspeaker. Browse loudspeaker. Okay. Add data link. Okay. Now you see we have created the link. We take electric forces from electric problem. Now save all problem files and run the analysis. Oh, not enough boundary conditions. Well, what does this message mean? We have the force acting on the diaphragm, but we do not specify any fixed point of the diaphragm, so it can move freely in any direction. Let's fix the diaphragm. I believe I will fix it here. Click this edge and assign label fixed. And for this label I specify 0 displacement in both directions. Okay. Now let's solve the problem. Oops, and another error message. The linked problem results are out of date. Again, what does this mean? Remember, both electric and mechanical problems share the same geometry model file, and we have modified the geometry model. We have assigned label to this edge. We have provided physical properties for this label in mechanical problem, but we should provide physical properties for this label and in electric problem too. This edge has no physical meaning in electric problem, so again I do not specify any properties here. Just click OK. Anyway, the problem setup has changed and we should solve electrical problem. Well, I believe the results are the same. Now let's solve the mechanical problem. Let's take a look at the results. Here on the field picture you can see the column map of von Mises stress and the deformed shape scaled 10 times. And the maximum displacement of the diaphragm is 0.1 millimeter. If you search for the electrostatic loudspeaker on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.